think everyone in the room will agree that R is a very active community. Some of the best data scientists, statisticians, mathematicians out there. It's also had, over the last 2 decades, a very healthy and steady growth. But year after year, I hear, can R scale? Can it deal with very large data sets? So that's what we're here today to do, to talk to you about how you can scale your R workloads on Google Cloud. Our agenda for today will be talking about the evolving R ecosystem on Google Cloud, 3 reference workflows for training and serving machine learning models. 1, TensorFlow, 2, Spark, and any R library that might be a favorite of yours. Finally, we'll close with a Q&A with an online Dory app. What is a Dory? Well, it's a Q&A messaging app that we use internally for Q&A at scale to make sure everyone has an opportunity to ask questions. If you go to our Google Cloud Next app, find our session, you'll see a Dory Q&A link. This will allow you to compose a question as well as vote to move the good questions up to the top that you want to see answered. This will actually be open for the entire week, so if we don't get to all your questions, we'll make sure to answer them directly in the app itself. So let's get started with the R ecosystem on Google Cloud. I posed a question around, can R scale? One response might be, does it really matter? Is there enough demand for it? So 2 areas to really look for are distributed data processing as well as deep learning. 2 workloads that require lots and lots of computation. And if I do a quick analysis on CRAN logs, the number of CRAN downloads, from 2017 Q4 versus 2018 Q4, TensorFlow and Keras libraries, 2 deep learning frameworks, have doubled in usage. This really is a signal that data scientists are exploring deep learning to solve new novel ideas in new problem domains. Also, SparkR has actually grown by 6x during that same time period. A great signal that data scientists are really pushing the limits of one machine and the memory that really restricts you to, and looking for distributed options on clusters. So Google Cloud should scale. I've been in Google Cloud for 2 years, and I will say I felt neglected as an R user. Of course, as a cloud provider, developers were our primary audience. We want to make sure that developers can build applications on the cloud. We provided client libraries like Java, Node.js, Golang. Next, we needed to help data engineers build these pipelines and data stores, providing a SQL interface, maybe a Java API for big data frameworks like Apache Beam. And then finally, TensorFlow is still central to our ML ecosystem. So naturally, Python was a first-class language choice for ML engineers. But after 2 years of feeling neglected, I really am happy to talk about some of the evolution of Google Cloud to support the R community. Natively, we do have a lot of notebook options now. We also give you options to run Spark on a managed auto-scaling Spark service, allow you to train TensorFlow models or any custom R library models, and really a big thanks to the overall community. There's a lot of packages that have been contributed from Mark Edmondson, Hadley Wickham, and the RStudio team to really interface to a lot of the great big data and ML services that Google Cloud has to offer. So let's talk about how this actually looks like. At the very top, we have lots of different notebook solutions. Zeppelin, everyone's favorite RStudio, RIDE RStudio, as well as a managed Jupyter notebook with an R kernel. Then moving to the very bottom left, we have ingestion and storage options. The 2 main ones we'll cover today are Google Cloud Storage, our object storage service, really for unstructured data, working with images, free text files, audio samples. And then for structured and semi-structured data, we have BigQuery, our petabyte-scale, fully serverless data warehouse. As we move more into exploratory work and data profiling, what are options to explore and prepare that data? We have a SQL syntax on top of BigQuery that allows you to crunch through billions of rows. We also have Spark, again, the managed auto-scaling cluster that I talked about, if you want to use some of the more statistical techniques like PCA or dimension reduction techniques that are available through Spark's native MLlib library. Now, this is where things get interesting. Usually, I would move on to the right side and build a custom ML pipeline. But I do want to stop and think about the bottom middle there, where before you invest time in that, you should actually look into if some of our pre-trained APIs can offer up some solutions that can get you a good way there. We have a lot of different pre-trained APIs in the natural language space, the image space, translation, audio transcriptions, and we actually have a ML service built directly into our data warehouse, BigQuery. And on the right side, this is where we have invested and we believe we can add value in building a robust ML pipeline. And the 3 workflows we're going to cover today are TensorFlow and Keras on a managed service called Cloud Machine Learning Engine. We'll have Spark's MLlib library outside of just the data processing techniques on Dataproc. And then the #1 question I've gotten over the last year is, what about any R library? I like to use my statistics libraries, my caret, my rpart? How can we use a container-based approach to actually run those at scale as well? So before I jump into the workflows, which we'll primarily focus on, I want to just give you also 2 quick examples of how to embed some of these workflows upstream. So let's say I want to query lots and lots of data. On the left side, I'm loading BigQuery query. This is created by Hadley Wickham. And with a few lines of code, nothing special, your normal SQL syntax, but this exact query actually crunched through 100 billion rows, 3.5 terabytes in 45 seconds. And then it downloads it as a data frame for you to then run ggplot and other various analytics and visualization on top. So very powerful for quick exploratory work, and really allows you to push all that scale work to our managed service and then bring what you need into our data frame. On the other side of things, let's say I work for customer service, and I want to analyze all the customer logs for sentiment and what are customers actually calling about. Usually I would need to probably go to school and get a deep learning degree. I would then maybe have to look for word embeddings and understand the relationships between the different words. I haven't even gotten to creating a labeling data set that is required for machine learning. So before I invest in all that or hire a team member who can do that, here's a few lines of code where you can access our natural language API, the Google Language R API that was contributed by Mark Edmondson. It allows you with a few lines of code to analyze the text, extract various entities ranked by salience or importance, to classify the text into various categories, as well as then look at various sentiments. Now, this might not be your end-all, be-all. This might be an upstream data enrichment exercise where you then combine some of these outputs with some of your structured data to build a more traditional structured data model. So now let's dive into the actual workflows. And the first one is TensorFlow. The RStudio team has been working alongside our TensorFlow team to really build a great set of R APIs interfaces on top of the TensorFlow Python modules. On the very left side, we have our 3 core R packages. Starting from the bottom, we have TensorFlow. This is the lowest level API that allows you to build the graph of operations, gives you the most flexibility and customization. Moving on to the middle, TF estimators. This allows you to use out-of-the-box algorithms, regression, classification, some of your common neural net architectures, as well as even moving into spaces like support vector machines. And finally, we have Keras, our top-level, high-level API that's really built for usability and quick prototyping and rapid experimentation. And then on the right side, we have a lot of complementary supporting libraries. We have TF datasets. A lot of times when you're building a machine learning model, the training process doesn't always have to be your bottleneck. It might be how quick you're feeding all the data in the appropriate file formats. So TF datasets allows you to work with different file types to look at data parallel pipelines. TF runs, tracking, visualizing, monitoring those loss curves, looking at evaluation metrics. For those of you who have explored TensorFlow on Python, this is very analogous to the TensorBoard tool directly in your R UI. Third is TF deploy. While you'll use R to build and train your TensorFlow models, one of the main powers of TensorFlow, it is a language agnostic system, a framework where any other downstream application, whether it be Java, C#, can all consume all those predictions. So TF deploy allows you to export and manage and save all those models moving forward. And then finally, our core library, CloudML, is an interface to Cloud Machine Learning Engine, a managed service that allows you to provision a cluster of machines with GPUs or CPUs, as well as also hosting the models as cloud endpoints for you to consume in terms of an instance level or batch level prediction. So what does this look like in a more holistic architecture? We do have RStudio Server Pro available with one-click deployment through our GCP marketplace. The code can be version controlled within a cloud source repository. This is a private Git repo, but you're welcome to use GitHub or Bitbucket as well. Once you package your TensorFlow, and then let's say we're working on a deep learning model, we would store all our images in the bottom left there with Google Cloud Storage. Then we'll package the TensorFlow code, and the main piece here again is you might be doing light development work on the environment your RStudio notebook is based off of, but you're gonna actually submit the ML training as a job to Cloud Machine Learning Engine. You'll be able to only provision resources for a number of minutes, a number of hours with the appropriate hardware accelerators that you need at that time. So it's a very job-focused mindset from an always running development environment. Next, we're gonna save and store our results as well as our model binaries in Google Cloud Storage Bucket in a hierarchy of your choice to really version them as needed. And finally, ML Engine also has a secondary module for serving. This is where a model essentially automatically gets containerized and hosted as a cloud endpoint for you to be able to access as a REST API for instance level one-time predictions, maybe for a web or mobile application, or if you need batch predictions for running through millions or billions of rows of a table, you can run the batch option as well. Also interestingly, ML Engine is a cloud-based solution. You have to be connected to it. RStudio Connect actually is a very similar offering where you can maybe host that on-premise on a server as well and host some of those models where you might use our burst compute to train the models, but then still want to serve them on-premise. And then finally, the API call can be consumed by various downstream applications, whether you stay in the R ecosystem with R Shiny or other mobile and web applications. Let's dive a little bit now into the actual code. For training on Cloud ML Engine, again, just loading the Cloud ML library. CloudML_train is the main function where you actually just point towards your TensorFlow code that's sitting in a R file. There's a lot of optional parameters, and this is really where the power is. The master type, or the scale tier, allows you to access those resources for only the time that training is taken. A standard GPU gives you access to a NVIDIA K80. We have a P100, that's also an option. But if you actually want to even scale further and have multiple GPUs on one machine, we have up to 8 V100s on one virtual machine with a complex large model there. So with quick plug and play, you really have access to various choices to really optimize both price as well as performance when you're training models and thinking about this on a job mindset. Next, we have deploy and predict. We're going to load the CloudML library once again. Once you've really trained the model, you're going to have a directory where that model is saved. You can export that model. In this case, I'm calling it saved model. And then I'm going to deploy it and host it as an endpoint. In this case, I'll call it Keras MNIST. Now, at that point, you have a lot of different options from downstream applications. But if you wanted to run batch predictions or sample predictions directly in the R environment, you can use the CloudML_predict options to cycle through and see whether the images are being predicted correctly, whether audio samples are being transcribed correctly, or any other traditional structured data problems that you may be solving. So the great thing is JJ Allaire from RStudio was actually at Next 2 years ago introducing a lot of these libraries. So this has been around for almost 2 years now. So this is a rich ecosystem where RStudio has actually great resources, tutorials, galleries, samples for you to take a look at various use cases across industries. Everything from healthcare to traditional time series forecasting, which gets to boost with deep learning techniques, as well as natural language. So please check that out. And this is probably very mature currently out there. So now I'll kick it off to Chris to talk a little bit about Spark with R on GCP.
Thanks. So I am Chris. I'm a product manager here at Google Cloud for our open data and analytics team. And I'm here to talk about how Spark, combined with Cloud Dataproc, can help you scale your R analysis. Now, if you're not familiar, Cloud Dataproc, that is our managed Hadoop and Spark service. And many of you probably hear the word Hadoop and zone out instantly, thinking, OK, that old legacy technology. And that's valid in some ways. But Spark is still a very active community for machine learning. In fact, in like 2 weeks right here, there's going to be a Spark AI conference. And the reason why, it's because Apache Spark, it's a computing framework that lets you scale across a cluster of computers in a generalizable way. And that's perfect for building a rich ecosystem of ML libraries. And the other great thing about Spark is it lets us write our R code. And that means that Cloud Dataproc can scale your existing R analysis without requiring substantial code rewrites. Cloud Dataproc is often the fastest way to move your analysis and ML with R into the cloud. So our goal with Cloud Dataproc, we want to let you take the open source tools, algorithms, and programming languages like R that you use today, but make it easy to apply them to cloud-scale data sets. And then you can do that without having to manage tools like clusters and computers. Now, there's 3 ways to run R on Dataproc today. There's RStudio, which is the standard web IDE that can be auto-installed on the Dataproc masternode. And then there's 2 different packages for running R on Spark, SparkR and SparkR. And they have a lot of similarities, but there's some differences that I'm going to explain as well. So SparkR, that's a package for working with R on Spark that was developed by RStudio. So you're going to see a lot of great hooks and integrations between RStudio and SparkR. SparkR, that's built directly into Spark itself. And so you're going to find great hooks there with things like Cloud Dataproc's Jobs API. And that Jobs API, that makes it really easy to submit jobs through submit R jobs through things like the gcloud command or an HTTP endpoint, so you can build automated tooling around your R code. But what I'd like to do now is just take a quick peek under the hood of both SparkR and Sparkly to help you understand how these tools actually scale your R analysis. So this is a very high-level SparkR architecture. There's two pieces to Spark. There's going to be the Spark driver and then the Spark workers. Again, very high level. But oftentimes, this Spark driver, depending on what mode of Spark you're in, that's often going to run exactly where your RStudio is running. And you're going to spin up what's called a SparkR context. You can think about that essentially as a client for calling into Spark. Now, under the hood, what happens in that SparkR context is there's a bridge. It's done over a socket layer that's going to translate your R code into Java code. And then there's a Java Spark context that's actually going to scale your work across the various Spark executors. You can think of those basically as nodes in the cluster at a high level. Now, what's going to happen from those Spark executors is it's going to actually make a call out to a local version of R. And so that's real R. That means any package that you can take with R and scale, you can scale with SparkR rather, because this is real R code that you're running at the once it's broken up. Now, alternative architecture to that is SparkR. Now, what SparkR does instead is they're going to serialize the information into Apache Arrow, and that means in terms of ML algorithm. And then what they do is they use that information to call out to the spark.ml package. So that means in terms of machine learning, you're going to be limited to the functionality that exists in the spark.ml package. So there are despite that, there are some pretty cool features I found with SparkR that are missing from SparkR. So for instance, they do have a direct integration with CRAN. They have an XGBoost extension. And they also integrate with Broom. If you're not familiar with Broom, it's a pretty neat ML package that takes the output of a lot of unstructured, messy data sets. Like if you have a bunch of t-tests and it comes back as a bunch of unstructured information, Broom will take it and turn it into a nice, tidy data frame that'll let you look at results of multiple models at once pretty quickly. It's interesting. So of course, this is going to beg the question I'm sure everyone has right now. OK, what do you want me to use, SparkR or SparklyR? So SparkR, I find that folks use it a little bit more for automation. First of all, it's built into Cloud Dataproc and to Spark itself, so you get a little bit better performance. But SparklyR, again, that's coming from the tidy RStudio team. So that does tend to have a little bit better integrations with RStudio. SparkR, that comes from AmpLab, the same people who did Spark. So you're going to find that they are going to follow things in a little bit more Spark-first kind of way. In other words, it's going to follow mostly the Scala way of doing things, whereas SparklyR, they think a little bit more R first, and then sometimes they'll do an R integration at the sacrifice of something like performance. But both are active projects, and so when there are examples like that, what you find is they tend to get resolved pretty quickly. So oftentimes it just comes down to where do you want to spend your time? Automating R code, SparkR, or is it working with interactive RStudio type analysis, and then you go SparklyR. But if you're still a little confused on the difference in what to use, don't worry, I probably am too, but luckily I found it's not really an issue to use both. So once you load the SparklyR package, you can then just call into SparkR. It does step on some of the dplyr functions, but as long as you mask it correctly, you can go ahead and use both. And a set of code that has both SparklyR and SparkR can be submitted to the Dataproc Jobs API. So what I'm going to do now is I would like to quickly walk through an example of how you can use Cloud Dataproc to scale some R analysis. And what I'm going to show you is a common model like the one that you see here, where we're going to run through a workflow where the data starts in BigQuery, which is often a common store for semi-structured or structured data sets. We're going to spin up an auto-scaling Cloud Dataproc cluster to actually do our machine learning. And then we're going to save the output of that model into Google Cloud Storage. And that way, later on, when I want to rerun this, I'm going to use a Cloud Dataproc workflow template, which is a set. It's basically a graph of jobs that you can send to Dataproc. It'll spin up a right-sized cluster to run those jobs, make sure that the cluster is torn down, and then save all the output of what happened and all the logs into Stackdriver. So, Mikhail, do you want to take over on your laptop? Flip over? OK. Go ahead and kick us off. OK, so essentially, I'm a product manager here at Google Cloud. So a lot of time I spend essentially building articles or blogs that I put out onto the internet. And what I'd really love to have is a machine learning model that would read my blog and then say, how successful is this going to be on the internet? And that might give me an opportunity to go back and tweak some things before I actually go and try to publish it. So whenever I'm looking for data sets like this, I always start with BigQuery's public datasets program that has over 180 different publicly available datasets that are stored for free that I can take and use to augment my analysis. And what I do, and what I'm doing here is I found a great dataset for Hacker News. And Hacker News dataset, it has basically a score, which is how well that article did on the internet. That score is a combination of upvotes and relinks. And it also has the full text of the article, so I can use that to train. Now, what you're seeing in this query here is just I'm taking scores greater than 0 and a length of text greater than 0, only to get a nice, clean data set. Because what I'm trying to do here is, although BigQuery is awesome at SQL, I want to take advantage of R and some of the machine learning capabilities that Cloud Dataproc can offer me. So what I'm going to do is just going to put this into a table. I could go directly with the query, but I'm just going to make it easy on myself and take a 1,000-row sample and just put it into this Hacker News sample data set. And you can see in the bottom of the screen here, you can see what I'm getting back, which is a score that I'm going to use for a label, along with the full text. So once that job has actually completed, what I'm going to do is I'm going to jump back over to Cloud Dataproc. And I'm going to click on my cluster, and I'm going to come into a web interface. Using our component gateway, we expose various web UIs that are running on your cluster, and then we make sure that you can come into those using your Cloud IAM credentials. So you saw me just jump into Zeppelin, which is a Spark-based notebook, but it also can work with R. And so the first thing that you're seeing me do here is just that same query I ran in BigQuery. I could have run that directly in Zeppelin. There is an interpreter, so I'm just showing that. But what I'm doing, what I really want to do is I'm going to run this Python function that's going to let me take that an arbitrary tables of my Hacker News sample and pull that into a Spark data frame. Now, once that's into a Spark data frame, I'm just going to do a quick count to establish that, hey, there's 1,000 rows in that sample. That matches my limit, so I'm probably on the right track. Now what I want to do is I'm going to register this data frame. And so that, with one line, I'm going to register my data frame as a temp table. And that's going to let me work with this same exact data frame across all the languages of Spark. So that's Scala, SQL, Python, R. I can go back and forth without having to move infrastructure or data around. It's all in the same data frame. And you can see now that I can start to do some of my basic R explorations, things that look completely normal, like filtering on data for scores greater than 50. But I can now do this on cloud scale data sets instead of just the R that's running on my laptop. Now there's two ways I can actually scale analysis using Spark. First off, this is an example where I'm just going to send a GLM across Spark and send it with a lot of different hyperparameters. So I can tune a lot of smaller models at once with different hyperparameters, get those all in a list, and then analyze which model maybe performed the best. But in this example here, I'm actually not going to do that list apply. I'm going to do a dapply, because I just want to run one NLP package that I love in Spark across that whole data set of Hacker News. Now in this case, I just have my 1,000 samples that came back, but this is enough where I'm saying, yep, I think I'm on the right track with this model. So what I want to do now is I'm going to go back up to the function where I was calling my sample table. And I'm now going to change that to the full Hacker News data set, so the entire corpus of notes, not just my sample. And then just by clicking this off, I'm going to rerun all that same code you just saw, except this time on the full Hacker News data set. And as this kicks off, what I want to do is come back into Dataproc and take a look at what's happening underneath the hood. So I started with 3 VMs, which is totally fine for my 1,000-node sample as I was manipulating the data and getting ready. But about 2 minutes later on the large data set, as I'm pulling that data in from BigQuery, the Dataproc autoscaler says, hey, you need a little bit more help. Let me add a couple nodes to your cluster. Then, a few minutes later, there's another spike in the yarn memory usage, which is because I'm actually now training on that text data. So the cluster got even bigger. But once that model training completes, I just refresh the page, and the Dataproc autoscaler has said, OK, I've used all the memory I need, and it scales my cluster back down for me. And so all of that was able to occur without me ever changing from the notebook. I didn't change environments. I just clicked Run, and Cloud Dataproc autoscaler knew how to respond. Finally, if I wanted to save this model off and not keep a running cluster, but have something else around, have it around, I could create a workflow template. And I'm not going to step through all of the steps here, but essentially, it would end up looking like this in the console, where at any time, if I wanted to rerun all this with the associated cluster, I would just click Run, and that would be it. All right, we can flip back to the slide deck now. So if you want to go and get started and do that exact same analysis, this code is what I use to spin up the cluster. It's pretty straightforward. It's just I'm calling into Cloud Dataproc. I'm saying use the optional components of Jupyter, Zeppelin, Anaconda. In this example, you could also throw in RStudio. I used Zeppelin because I wanted to go cross languages, but you could definitely use RStudio with this initialization action. And then I installed a BigQuery connector. And the enable component gateway, that's what exposed those web UI links for me and made sure that I had permission to get into them. And finally, the auto-scaling policy. You can actually tune the auto-scaling policy to, there's a lot of knobs that we expose. If you don't care about those knobs, you don't have to use them, but they are exposed if you want to tune the settings of the autoscaler to how aggressive you want it or how often you want it to scale. So with that, I'm going to hand over to Greg.
All right, thanks everyone for joining us this morning. So we heard about some great ways to leverage TensorFlow and Spark ecosystems using R and GCP, but what about the cases where you need to train and deploy a model using any R library? So let's look at an end-to-end solution for this. So first we need to set up an R development environment, and Cloud ML Notebooks is a great tool on Google Cloud for data scientists to do this. We can get started with one click, easily scale up with compute engine machine types, add or remove GPUs as necessary, leverage both R and Python from the notebook, and enable team collaboration with Git integration and Cloud AI Hub. We can publish notebooks to Cloud AI Hub. Specifically for R users, we can get started in 4 steps. So we can launch a PyTorch ML notebook, which has Conda installed. And this is going to make it easier to install our R-based package and libraries. We're also going to load the RPy2 extension to enable R cell magic. And this is what allows us to run both R and Python in the same notebook. We're going to create a directory in our home folder for libraries so we can install our own libraries and have write access to that directory. But what should we do in those situations where resources on our development workstation aren't adequate, like running out of memory when working with a large data set? So let's look at how we can package our code in containers for running on Cloud ML Engine and Kubernetes Engine. For those just getting started with containers, you can think of them as a method for packaging an app with its dependencies for running on a variety of platforms, not just on ML Engine. So in the next demo, I'll walk through building a pipeline based on this architecture. We're going to import and analyze our data with BigQuery. So we're going to use standard SQL to query our data set, stage it as a CSV file in Google Cloud Storage. We'll write a training application with Jupyter, with ML notebooks and R, and we'll package this up with Docker and send it over to ML Engine. We'll write the app such that the assets the model assets that are created by the training app or stored in Google Cloud Storage. And we'll take these assets and package them in another container that we can deploy for serving. And this will leverage Google Kubernetes Engine, Seldon, and S2I. All right, demo. All right, great. So first we'll navigate over to ML Engine and ML Notebooks. I already have, or well, we could create a new instance, PyTorch, but I already have one created, so we're going to open this one to start. And I pulled some code from GitHub, so I'm going to start here with a notebook I've already created. I've used Conda to install RPy2 already, so I'll go ahead and load the extension. I've created a directory for my libraries, and I can go and check this out and see that I've installed some already and I have access to them. And then I can use the RCell magic next to install whatever library I need. And then we want to get data from BigQuery, so we can use the BigQuery cell magic, and then our data will be exported into a data frame, which we can then import into R. So then once it's in R, we can view the structure of the data that we've pulled in. Here we're looking at public baby weight data from BigQuery. And we can also build a model, just a traditional linear model, just to get started. But we want to do more than that. So let's take this data and stage it in cloud storage so that we can run some other models, and we can scale it up to ML Engine. So I'm going to go into the BigQuery console and take that query and paste it in there. And this can be done from within R using the API, but it's just as easy to use the console. So first, I'm querying about 68,000 rows just for testing. So I'm going to have two CSV files. And I'll export this directly to Google Cloud Storage. And this is my storage bucket. The train data small is going to be that file. And then I'll change this query to sample a bit more data. And we'll use this data set for when we scale to ML Engine. So when this finishes, we'll see that we have about 13 million rows. You can also see that we're doing a little bit of pre-processing in the query. And it's good to keep in mind that BigQuery is very performant for pre-processing data with SQL. So this would be a good case to use SQL for some of that instead of R, potentially. So we'll export this CSV to cloud storage. And now I've got my data staged for training. So I'll head back over to Jupyter, and I'll start working on writing my training app. So first, I create this trainer folder that you can see on the left sidebar there. And I'm going to create a file for installing my R dependencies. First, I'm going to set a library path based on an environment variable, and then I'll specify the packages I need. And then in the training app, I'm going to specify that same library path. I'm going to configure command line arguments for Google Cloud Storage for training data for the export directory. I'm going to use caret to impute missing values, center and scale my data. I'm going to change the factors or the features I need to factors, partition the data into test and train, set up hyperparameter tuning, cross-validation, and then I can kick off my training job using GLMnet for this example. And when the training's complete, it's going to save my model file as well as my pre-processing weights to Google Cloud Storage. And I could also export any additional assets that I wanted, like if I wanted to export plots or other results. Then I'll go into Docker to package all of this. I'll take the base R image, I'll install the Google SDK so I can download my files from cloud storage. I'll copy over that file or that script to install packages, set the library environment variable. I'll copy over the training app, and then I'll use entry point to tell ML Engine, hey, this is the script that's going to run when the container kicks off. So before we go ahead and deploy the container to container registry, let's just make sure the training app runs locally. And then we'll get the model file saved. And then we'll also test inference. This is an end-to-end deployment, so we want to make sure inference works as well as training before we go ahead and start training on ML Engine. So we see we get a result returned. So we'll go ahead and build the Docker image and package up our training container. And then we can deploy it to Google Container Registry. And once it's in container registry, it's accessible to ML Engine. So we'll submit a job referencing that container, reference our training data in the storage bucket, the output directory, and we can also specify a machine type or a cluster of machines here with accelerators if necessary. So when the job is submitted, we can go back over to the console and use ML Engine to view the job running. We'll be able to see our utilization metrics and our logs. And you can add additional logs as needed, based on your training app. When the model is complete, the model assets are written to cloud storage. So we can go into cloud storage and see the assets from the prior jobs that have run. So I've got a few folders here from prior jobs, and we'll look at the most recent. And here we can see the model RDS file and the pre-processing weights. So then let's go back into Jupyter and let's serve our completed model. So we're going to install S2I, which is source to image. It's a tool that's just going to make it easier to build the container image without a Docker file, essentially. Source to image and Seldon require this environment file. It requires an install.r file, which installs the dependencies. We're going to download the model assets from Google Cloud Storage and include them in the container. And then we're going to set up a runtime file, which is going to load the RDS model file, the pre-processing file. It's going to take the input from prediction, do the pre-processing, and then evaluate against the model. So once we have all these files, we can call S2I to build our serving image. So very easy. We don't even have to build a Docker file here. We just build our R files for serving and then package up our image. We can test it locally and then run a request against it locally. We see we get what we were expecting. So we can also view logs if we needed to debug and then stop the container to restart it. So we'll go ahead and push the working container that we have to container registry. And if we didn't have a cluster already started, we would create one, a Kubernetes cluster. And we can see that we already have one running. So we'll deploy the application to the cluster we have running, and then verify that it's been deployed and that the pod is running for the application. And then we'll expose the deployment on port 80, and then get an external IP address for the app. So we have our external IP address. We can make another request, and we see the result we were expecting. So it looks like we're good to go. A nice thing with Kubernetes Engine, our managed Kubernetes service, we can go into the console and view the pod, the application running. We can see utilization metrics, and we can view logs from the container as well. So with that, I'll pass it back over to Mikhail to wrap up for us. Thank you.
Thanks, Greg. So just in closing, hopefully this image makes a little bit more sense. I think at the very top, starting with the notebooks, I think some of the key ways we saw Chris talk about the new web interfaces module within Dataproc that allows you to quickly spin up these notebooks. ML Notebooks actually is a managed Jupyter service that went also beta on March 1st, so also a new service that maybe a lot of you may not have heard of before. But we really made sure that both demos as well as my reference architecture showcased all three, so you got a sense of how each of those three look like. We also walked through different storage techniques, both from BigQuery as well as GCS. And from a Spark perspective, I think the auto scaling is something that I've really been using quite a bit myself, as well as working with a lot of customers, because there is no need to then necessarily right-size your workloads or maybe have a little bit more capacity than you need sitting idle. That auto scaling feature really has certain logic built in when the number of clusters grow. And then on the very bottom right, what Greg walked through, we'll make sure to provide that in terms of GitHub code. But the key takeaway is, again, hybrid and portable. These are all containers. You can use them on Google Cloud. You can train or create a serving application. But those are fully portable to be ported over to another cloud, onto on-premise. And Seldon specifically, the serving approach that Greg walked through, that's part of the broader Kubeflow ecosystem where we are making it very easy connectors to the Kubernetes ecosystem. A quick cheat sheet around both the services and libraries. It is quite a bit, and we'll try to get some resources out there online. But the first two rows really talk about the data ingestion GCP services, as well as the R packages that allow you to access these very quickly directly in R code. We walked through different ways of doing that within your R code, as well as directly in the console, whatever you're more comfortable with, various options there. And then the bottom three talk about the training service, the serving service, and then the actual R library packages that you can leverage to access that in a familiar environment. Now the last column, of course, that does require a little bit of container knowledge, Docker, Kubernetes, but really does future-proof yourself and makes a lot of your R workloads portable moving forward. So what now? We have a couple of bit.ly links for the Spark ecosystem. Chris did publish a blog post a few months back. That's a great primer on how to get running with Spark on Dataproc. TensorFlow.rstudio.com is a great repository for resources. And RStudio and JJ actually partner with the creator of Keras to publish a book, Deep Learning with R, as well as the great cheat sheets that RStudio is known for. And then I mentioned the examples that Greg walked through, a lot of great information. The GitHub link is there under G. Mikels, his GitHub name, along with Google Cloud R examples, as well as some bit.ly links for a new feature within machine learning engine as well for custom containers, as well as Kubeflow and Seldon.